I will organize this presentation in such contents. First, I will give you some background information. And then we will introduce some premises of our research. And then go with the workflow of the generation of building model, navigation model. Sorry. And then some examples of our tests. And then I will wrap up this presentation. First, I would like to introduce what is navigation model. And basically they have three categories. Most popular one is geometry models, which means you have details of building geometry. And based on that, you can get logical models, which represents the topology of building parts. For example, you can have connectivity graph, and adjacency graph. And based on logical model, we may want to know what is the meaning of the building part. Then you may come some semantic models. By semantics here, it comes from ontology term, but we just use it as semantic notation of different building parts. So in different semantic models, you may define different building parts in different meanings. For example, we can define this auditor ring as an auditor ring. You can also define it as a room or something else. And for corridor, you can see it's a passage. You can also see it's a corridor. That's about semantics. And what we will do is we have a lot of data from pure geometry. We have geometry models. Then we want to know how to use this geometry to get navigation models. We have been seeing a lot of works on regular structure building, which is quite relatively easy to get the topological model or logical model. But here comes the difficulties. Is sometimes we may meet some complex indoor environments, which can be intermediate floors, or some non-horizontal floors, or some irregular shapes in large rooms. So in this case, we may need some specific subdivisions. And with different subdivisions, you have to explain what type of meaning of such subdivision. So here I give you an example. You can see from the top. Here is so-called intermediate floor, and I don't know how to name in a unique way. It seems a little complex because it's in a large room, large open space. So we may subdivide such a space into different pieces, and then you got the clear topological relation. By subdivision, we can categorize them into two parts. First, we would like to do is semantic subdivision. For example, we try to give the meaning of specific building part. We can see this is the reception area of a building in the front of the entrance, and we could see that is a multi-corner in the first floor. But also we can abandon this tags and to say we just need some regular or irregular geometry subdivision, which could be we use grid model and use each grid to track the people or robots in space. Or we can use voxel, to consider the height information much more. Or even we just use a triangulation to get the different triangulations without a specific meaning. What we do is we face the basic main two challenges. The first one is if we want to get some topological model, we may need to subdivide them. The best way is always be automatically get them. But even you got subdivision, some kind of subdivision, as I said, you may get different semantics from different semantic model. Then how you do with that to get a standard way or unique way to get your navigation model. Unfortunately, we didn't find some of reasons on semantic subdivision automatically doing that on available building data. By available building data, we could consider, for example, CGML, building information model, IFC+, or some other just CAD files you draw from floor plans, which could be a pure geometry data. So we want to rely on our previous work, which is called indoor navigation space model, INSM for short. Basically, it follows the original structure of the spaces. I will introduce this later. But here I will give you an example similar to the previous case. And I will ask you a question. How do you think how will you name such different parts? For example, if you in the middle part, how will you call it? Any idea? Yes, middle part. Okay. I don't have a unique name for this neither. I don't know how to call it. And for the bottom part, it seems like just several steps. Should we call it a stair, or should we call it something else? I don't know. So, with such difficult description, we like to use IMSM to facilitate the description and the construction of logic models. First, I will introduce this model, and then I will explain why this model can fit for such a complex building part. So the model has some basic ideas. The three elements could be: first, we name this navigable space cell, which means a space you can freely move inside. And for opening, we means any openings or windows, doors, doorway, even you have no door panels, we call it openings. And sometimes we may face some obstacle, which means some obstruction volumes. It's kind of spaces inside of the navigable space cell. With the three basic elements, we can further subdivide them. So here you see a little stair. With such kind of vertical movement structure, we call it vertical unit. Oppositely, you can get horizontal unit, which means you can move horizontally on the space. And for horizontal unit, we still have further subdivision. We could consider one kind of them is horizontal connector, which means at first it's a horizontal unit, you can move horizontally, and it has a function to connect it at least two of other horizontal units. So it's somehow you can consider it's a passage, or it's a horizontal passage, or a corridor. And we have another type, we call it end, because and you can see this room, and this very big little room I made. We call it end because it's just connected with only one other room. If you go there, you either out or either inside. And the last type is we call vertical connector. It is a horizontal unit, but we call it vertical connector because it connects at least one vertical unit, could be stair, could be elevator, whatever, and it also connected to some other horizontal units. So with such different horizontal units, if we compose up of them, we will get such the notion we call it horizontal space. You can imagine that's floor things we always call it. But you may notice from this picture, we have different height of horizontal units, which means if we consider a given tolerance, we can compose different horizontal units to a horizontal space. It may not just be a flat floor. And sorry, I would like to go back to this picture, to the upper right picture. So here, I don't know if it's possible to call it a corridor or some platform, but I would like to call it with INSM, I would call it an end room, because this room just connected with larger room by several stairs. So we can easily call it end. And for this staircase, maybe it's too short to call it stair, but still we can call it a vertical unit. You move a little in vertical direction. So with this model, we can easily expand some different complex building environment. Even this model is proposed conceptually on 3D space, but we also can apply it on 2D or 2.5D. So here you can see the example. We just use the floor surface and the stairs to indicate the inside spaces. So we still got the vertical unit denoted by the stairs, and you also can see here are end rooms and horizontal connectors. So my point is we will not always use this for 3D. For some simple case, we still can band that with 2D. So here I just gave a simplified version of this model in UM classes model. My point is, if you got clear what is the navigable space cell and what is the opening, if we detect the relations between navigable space cell, which consists of horizontal space, a horizontal unit, and vertical units, and you have openings, if you abandon them, you can get the logical model easily and automatically. So far, I already get my background information. I will to say our goal is to generate the logical model. First, we generate it from the existing building geometry. We apply it on whatever data we got, and we will use the INSM model to support such generation. So here is a single workflow. We construct the INSM this model from the building data original table source, and no matter it's a CTGML, IFC, or some other data format, could be OSM 3D, or just a 2D drawing from CAD softwares, and we bind all the data to the INSM. And afterward, with our automatic method or program, we can easily get the logical model from the INSM. So that's what we will do for generation of navigation model. And another target is to summarize necessary preparations for automatic generation. By automatic, I just mean from the INSM, we can automatically get the logical model. But before that, sometimes we may need many work on that. It's not a solution for all kinds of cases. So we have to define some assumptions before. So as I said, we try to avoid the different subdivision criteria. So we choose the simplest way. We preserve the original angle structure as much as possible. Here I give an example. You can see this corridor. It's long and irregular shape, but still we consider it's a corridor. We don't do further subdivision like triangulation or grid on that to break it down. We don't do that. We just keep it as is. That's what we call following the original structure, and that's is what the IMSM do. And also, sometimes we need to give an explicit connection between some spatial parts. Here I give an example. You can see this parallel staircases, and with 2 more steps. And how do they connect it with the other spaces? If we don't have such indication of opening, we don't know if staircases can connect it with a horizontal part. So sometimes we need to explicitly indicate that. And for some pure geometry, for example, like the 2D drawings, we need to, if we want to get the topological relation easily, we need to detect them by comparing the geometries. For example, if we have a soup of polygons, we check if they meet each other or if they overlap with each other. Then we know if they are close enough or they are connected. After we got the topological models, could be connectivity graph, could be an adjacency graph, but we don't know the accessibility. We need some extra information. For example, if I don't know this room is locked or not, then I just give you connectivity. But if you say for a specific user, if you can enter into this room, I will check you and to check if you have a key of this room. That's the issue of accessibility. And here comes the workflow, how we generate this topological model. So from the existing building data, the first step is to clearly declare what is the subspaces, what is the room, what is the opening. And then we may add some attributes or geometry. For example, we can, for open space, it's connected to some other room, but without door, just have doorway. Then we may add the geometry, both 3D or either 3D or 2D geometry on the openings, or we just easily indicate they're connected. So we need such kind of information, and then we can get some initial result. But we will band this data or this result to IISM to enrich the subspaces. Because after this enrichment, we can use that for better navigation. And after INSM, we already know what is navigable space cell and what is opening. We know the relation between them. We can check the connection and finally get the topological model. So here I will give you some examples of our test. The first example is about CTGML data. The data source is come from we use reconstruction procedure from Dr. Marcos Gross, and which is supported by an indoor OSM project. The idea is we take a picture and mapping them in some edit tool, and afterwards we upload to OpenStreetMap servers to get the unique IDs, and And then we will have the data in OSM format. And then we output this to a database with the in-house program provided by Macros for us. We can generate CTGML data from that. So the whole story is from 2D drawing. We reconstruct it with some attributes data. We extrude these 2D floor plans to 3D models, and then write them in CTGML data format. So if we got the CTGML data, conceptually we can bind this CTGML to IMSM. So from the CTGML, at first we got the whole file as building, and for the room under the building, we will attach it to navigable space L. And since room consists of wall surfaces, and the wall surfaces will attach to will contain some openings. Then we get openings for INSM. And the tricky part is how to detect the obstacles. So we check with CTGML, and we find indoor building installation. It means some could be some objects like a pillow in the corridor, or some fixed things. So we call it fixed obstacle. And room can contain some building furniture. So we call them could be like desk, chairs, or some other things, a close set. So we call them a movable obstacle, which means you can take from one place to another place. And for both room and building, they have some building installation, or they get a clear tag called elevator or stair, which can be bind to a vertical unit in IMSM. So in such a way, we can convert the CTGML data to IMSM. And here comes the reconstructed CTGML file from Macros. Because this file is not strictly follow the specification of CTGML, the latest version, so we just play a little trick. We just trace the door and room information by their IDs. So here you can see, at first we got the door ID, we recorded, and then we trace back to see which wall surface contains this opening. And in this wall surface, it contains, in its name, it contains the room ID. So that's a connection between room and doors. If we check this continuously, we will get the whole building's room door relation. And from room door room relation, we can build up the connectivity or the connection between the different rooms. So here is a 3D model we constructed for the ODB building in Philadelphia. It's not perfect for this reconstruction. At first, we don't have the indoor furniture, like just the obstacle I said. We cannot reconstruct that. And another problem for us is we don't have detailed geometry of stairs. So what they do is reconstruct the stair or elevators as rooms. So what do we do if we want to have a vertical unit? So here is the trick. I add the words stair and elevator explicitly into the CTGML file, and then we check just with this tag or these characters, and to see if they are vertical units. So here you can see I clearly declare this room. We reconstructed it as a room, but I put the name stair for that, so I know it's a stair. And in this way, we can get the vertical units. And here is standard data from the latest specification. They have a very clear structure. So at first you can check the room under the interior rooms and even under the building. With the parsing, along the parsing, you can easily find opening in this under these rooms, and then you will find the door. So in such way, we don't rely on some ID, we don't rely on some words or characters. We just rely on this clear, defined structure. We can find the relation between rooms and doors, and furtherly, we can get the room-to-room relation. And finally, we got the logical model. No matter what kind of CityGM data we got, because CityGM LD4 data, there are not so many data on this field for the time being. So we could get different types of data, but no matter what kind of data we got, we do it in a general way, like this. So first, we fetch the data. We try to parse in the CityGML and get the rooms, get the openings. Then we match the rooms and doors. And finally, for afterwards, we for each opening, we check opening and room relation, just like here. We check for one door and check which room contains this. And after that, for each room, we know how many doors attached to it. And then we check from one room how many distinct other rooms connected by their openings. Then we know the connectivity between rooms. After we got the initial connectivity, we enrich it with IISM. For example, for each navigable space cell, we also can call it a room here because it's a simple building. And first we check if it's a stair or elevator. If it is, then we confirm it's a vertical unit. If not, we keep checking. If they connected to two other navigable space cell or two other distinct rooms. If no, we can see, okay, it's just the end. It just contains one connected with one or zero rooms. And afterwards, we check if it's connected with any other vertical unit. If it is, then it becomes a vertical connector. Because according to the definition, if you connect it with vertical unit, then the horizontal unit called vertical connector. And finally, we got the remainder as horizontal connector. They are connectors. They connect the rooms. They just connected with horizontal rooms. You may ask, what's the usage of this kind of enrichment? And here I will give you an example how it looks like when you do navigation. So first, we suppose we start from this room, and we will get a route until the entrance of the main entrance of the building of OTB. So here we start, then we move to a corridor, we call it horizontal connector. And then we move to the room just in front of the elevator, and we call it vertical connector. And then along this vertical unit, we will arrive to another vertical connector. And then we move into a horizontal connector. Then we arrive at the destination. So from this process, we could summarize a very simple pattern for path. If we move on the same floor, we would have a pattern like this, from an end room to a horizontal connector, to another horizontal connector, until you get your destination or another end room. But if you move between different floors, you probably like a path like this, from from an end room, and you enter to a horizontal connector. If you want to change your floors, you may you must pass the vertical connector, which means you choose one of the stairs or one of the elevators, and then you move to the stairs, the vertical unit, or sorry. Okay, I will be fast. And then you go to the vertical connector and to the horizontal connector to the and to the destination. So here comes our result from the ODB 3D building. We easily got a logical graph like this. You may notice it's a direction graph, which means we originally considered two rooms are connected with each other. And another thing is, for each edge, we may contain more than one openings on that, because like this room, if you have two doors connect to the corridor, we just consider it's one edge. And here is the result of the enrichment. So you can clearly see we emphasize the bigger nodes are vertical connector, horizontal connector, and these nodes are vertical units. They connected with different floors. It's quite clear, and if you got roof like this, you can easily subtract the structure. And here is another example from the floor plans. We just got a picture, the image. We have to reconstruct it by digitalizing in Bentley system. And we organize the data in different layers. For example, these rooms, we call it navigable space. We put them in one layer. And for the openings, maybe not really, for openings, we organize in another layer. And we also detected the topology by comparing geometry. For the vertical unit, this is stair, this is indicating the elevator. We distinguish them by slope. If almost the full vertical, around 90 degrees, we can recognize it as elevator. And in the same progress, we can get a similar result, and also emphasize the different parts and with different functions. So we can analyze the result. So for semantic rich and semantic poor data, apparently semantic rich data would be very helpful to get the topological result because for semantic poor data you have to do processing for further handling. And what about manual work? We try to save our effort on manual work to get automation. But here for CTGML, again, they have no clear definition of or indication on vertical building components. So you have to give them some kind of attributes or geometry. And for semantic pool data sets, like floor plans, we just showed, at least you have some semantics. You have to supplement them. At least you usually indicate which is the room, which is the opening. To sum up, semantic rich data is always better. You use that for to derive the topological graph for navigation. And it's better to follow the standard structure, especially for our CTGML, because currently we just conduct the two tests. We believe CTGML, if you follow the structure, that makes things easier and standardized. And for floor plans, there's no standard method. Like if you say, like in the previous case, we say this vertical slope or polygon, we call it elevator. But here you can see there are some walls, they are also vertical. If you set up the same rule for the different data, you may make unexpected problems. So, of course, we use our IMSM to enrich the navigation semantics, which makes our navigation easier. And in the future, I think And I believe semantic notations should be standardized, or some kind of a link should be set up between different semantic models. Otherwise, we don't know we are talking about the same thing. And for semantic models, I believe real data will follow the suggested structure, even you just made up some data from the original 2D geometries. And for CityGML, I would strongly recommend it if they can provide connection to floors, because they have very very vague definition about the floors or the elevators. They call it building installation, but could be outside stair, could be inside stair, you never know. Okay, that's the end of my presentation, and thanks for your attention.
Yeah.